Okay, let's get started. Hello, everyone. My name is Sahil, and welcome to this workshop on online resource allocation. So here's the agenda. It's a 3-day thing from 9 to 11 a.m. And so today are the tutorial talks, and then we have a bunch of invited speaker talks, 6 speakers. So the talk for today is, this talk is about online resource allocation, why it's like a fundamental thing. I'll start off with general things, and then especially focus on something called as the large budget setting. So first, let's even look at what is resource allocation. And I want to clarify why this is like one of the most fundamental problems. The problem is basically about you have a bunch of resources and a bunch of requests, users, buyers, you can call them whatever. You want to distribute these limited resources between these requests so as to maximize some kind of a value objective. And I want to say this is like a very fundamental problem. Like many people define economics as nothing but allocation of scarce resources between different parties. And this is precisely what resource allocation is. And so a bit more formally, you have n requests. So the parameters I want you to remember is I'm going to use n and m. N is the number of requests, and m is the number of resources. So your question is about allocating these m resources between these requests. And each, depending on how you allocate, you're going to get some different value. And the goal is to maximize the total value, which is also known as welfare and so on. And when I say online, the only thing that changes is basically these n requests are these n sequential requests or n online requests. So request 1 comes, maybe the bunny shows up, you have to immediately do some allocation to the bunny. Maybe you allocate the burger and the carrot to the bunny and so on. And then the next request comes, maybe the penguin shows up and something else. So as these requests come, you have to immediately make decisions without knowing the future requests. So there's a trade-off, there's an intrinsic trade-off, whether you get the value from the current request or save resources for a better opportunity in the future. And yes. So we'll make here the users online today. Yeah. And this is like a very fundamental problem, many real-world applications. For instance, like simplest classical ones are like you want to sell a house. That's like a single resource, you have a single copy, different people coming and making you an offer. Do you accept their offer or do you wait for a better offer afterwards? Like hiring a job candidate. These are like very single resource problems. With more resources like shopping, like say you even do grocery shopping or any kind of shopping, you have limited amounts of resources which somehow need to be allocated between these requests, users, buyers, whatever you want to call them. And like flight tickets, like many of them, you took a flight to come here. Like again, you have some these the resources here are basically the number of seats on an airplane and different itineraries and so on. And again, you need to allocate them somehow to efficiently maximize value or some kind of value. Value could mean revenue, could mean something else. Lots of scheduling problems, like you want to schedule, or network routing, you want to send some amount of demand from one location to another. Again, auctions, like there's another very big application, like all these big companies like Google, Facebook, and so on, trillion-dollar companies, they need to allocate these ad slots. The resources they have is the ad slots, and somehow they want to run auctions. Spectrum auctions, and like yesterday, maybe if you attended Tim Garden's talk, he was talking even about blockchains, like how you want to allocate these slots between different kind of transactions. And like this is like, as I'm saying, like very fundamental problem and with tons and tons of applications. So today, like our focus is more about the algorithmic part of this thing, like how this field has, this has led to like many algorithmic ideas and problems in theoretical computer science. So let me say this entire problem again a little bit more formally. So I want to say you have n sequential requests, where a request is basically a triple consisting of 3 things: the valuation, the consumption, and the decision set. So basically, whenever the next request comes, it tells you a valuation. I'm calling it a valuation. It's like a value function. Depending on how you serve this request, like what kind of a decision you take for this request, accordingly, you'll get a different value. So the simplest setting is maybe you like sell the house or not sell the house. That's a decision, like just a binary decision, but it could be like a matching kind of a problem. Like where do you match? That could be the decision. So there are many applications, and accordingly, you have a different decision set. And depending on what decision you take, you're also going to consume something. And I'm thinking of this consumption as a m-dimensional vector, because you have m resources. You might be simultaneously consuming multiple resources. So the question is, you're getting these requests, you want to maximize. So the overall goal is to maximize the total value, sum of the valuations. So ith request, I make some decision small theta I in the decision set capital theta I. So vi theta I, subject to my resource budget constraints. So summation over ai theta I needs to be satisfying all the budgets, B1, B2, and M resources. The problem precisely is challenging because you have limited budgets. So you cannot basically satisfy every request, giving it the highest, all the resources. So that's the main challenge. And I already talked about like a bunch of real world problems, examples in the last slide, but here's like a bunch of mathematical models or mathematical examples as well. So this is like a very classical problem, like already in optimal shopping theory, like in the 50s, 60s already, like more than 60, 70 years ago, this was being studied, like profit inequality, secretary problems. Some of you might have heard of things. They are more about like single resource allocation, I want to say, how to hire a secretary. There's like lots of thing that has picked up like in the last 2-3 decades is online bipartite matching. Lots of these problems like online advertisements and many others, they can be a very nice model for them has been online bipartite matching, where these requests basically represent maybe some kind of users who want to be shown some ads and so on. So one side of the bipartite graph is being revealed. Online routing is another very big example, like where you have some kind of a graph with some edge capacities, and your requests are basically some SI-TI pairs. You want to send some like unit flow from SI to TI while satisfying the edge request. So the question is, what paths do I take and what resources do I consume? Basically, the resource here is the edges, and so as to maximize as many requests. Online packing LPs, like packing LPs, is again a very fundamental example which has tons and tons of applications in real world as well, where you want to maximize some VIXI subject to like A transpose X less than equal to B. And here the columns of this matrix A, like AI, they are arriving one by one. As soon as ith request is revealed, you have to immediately set XI. XI is your decision set, so as to again satisfy the budget constraints. Auctions, combinatorial auctions, where these requests represents basically bidders arriving one by one. They are interested in subset of items. You want to allocate them. Again, a very big industry and lots of real world applications and lots of theoretical problems. So again, so these are just a small list, but hopefully all of you are interested in at least one of these applications, like shopping theory, bipartite matching, routing network design, or like packing LPs and combinatorial auctions. Yeah, so this is the basic model which we'll be focusing on. And there are like, again, many variants as well. But I think like this is one of the most fundamental. And in this model, we'll be talking about lots of settings throughout the workshop. Yeah, by the way, feel free to ask any questions if anything comes up between. Good. So in general, for resource allocation, there could be like many kinds of algorithms. One subclass of algorithms, which has been really, I would say, like very impactful, both in theory and in practice, is something I'll call posted pricing algorithms. It's kind of the algorithms that you run like at any grocery shop or any kind of shopping, where you basically put prices on the resources. You can take whatever you want, but you have to pay the price. So saying this a bit more formally, what's a posted pricing algorithm? Before the arrival of the ith request, so it cannot, like your prices cannot depend on what the request is. So before its arrival, you set a price vector. So it's an m-dimensional vector where the ith the jth coordinate, the jth coordinate represents the price of the jth resource. And now this request that came up, ith request, it's just going to take the best subset of these resources, which maximizes its value, which is basically argmax over theta in the decision set of theta I, the value minus the price. And what is the price? The price is basically going to be a dot product, like how much resources you consume multiplied by the price of that resource, just sum it up. So formally, that's nothing but the dot product of the price vector lambda I with ai theta. So just take the argmax of this, like the maximizing thing. So this is also like called as utility maximizing, best response. Like it has many names, greedy response, and often this is also represented by something called as the demand oracle. Often you assume that like these decision sets could be really complicated, like even exponential sized or even larger. And so one standard assumption which is made for theoretical reasons and to simplify things is like we'll assume some kind of an oracle access. That at least if I give you some prices, you are able to perform this simple optimization problem, which is, again, like as I'm saying, very useful and used a lot in practice, this kind of an algorithm. And again, to list out some of the benefits of posted pricing is, first of all, these are very fast and easy to implement in practice. So that's why they're like very popularly used everywhere. Another very major benefit is they are so-called truthful algorithms. So for applications such as auction design, where in these applications, these requests are coming from these self-interested agents who want to basically maximize themselves, like their own happiness. And they may lie about their valuation or like any of the other things, parameters, and you don't know, like you as an algorithm designer don't know their valuation functions. But this algorithm is great, the posted pricing algorithm, because it's saying that basically the allocation I'll be doing is anyways in some sense maximizing your utility. So you might as well kind of cooperate and like basically maximize, because I'm also going to maximize your thing. So that's why these algorithms they imply immediately truthful algorithms. And for many of these auction design problems, especially, they are very useful. And other benefits of some of these posted pricing mechanisms is they are often like robust to like some outliers and so on. And they're often even learnable from samples. These are things that we'll be talking about during the workshop. So what I want to say is like, okay, online resource allocation, first of all, is like extremely important problem, both in practice as well as in theory. And this is a large class of algorithms that are very commonly used, these posted pricing algorithms, which we'll be most interested in. But of course, like sometimes we may not be able to design a posted pricing algorithm, and we'll explore other ones as well. Good. And of course, the biggest issue with posted pricing algorithms is how do you set these prices? Like if you set a very high price, then maybe nobody will use your resource. Nobody will buy your resource. If you set a low price, then some initial requests will take that away, and the future valuable requests are going to lose it. So the entire challenge is how do you set or update these prices? And that's still a very, like a priori, a challenging problem. Okay, so again, this is why I was saying like online resource allocation, why it's like so important, but let me also clarify why it's algorithmically so rich, why there are like so many models and why it's like such a big field in itself. So some of the things that make a huge difference is, one is the budget size. Like each resource, do you have kind of like a single copy or you have many copies of resources? Accordingly, you might be able to make a few mistakes or you cannot make a few mistakes. And maybe similarly, are you getting like a 99% approximation, or are you getting like a 10% approximation? So those things will matter a lot. How general are your value functions? Like, are these simple, like additive valuation functions, submodular, subadditive, arbitrary monotone valuation functions that entirely, again, can change the settings and the kinds of guarantees you can get? What's the arrival process, like stochastic, i.i.d, adversarial, random order, like many of these things? What about the distributions? Do you know the distributions, or do you not know the distributions? Do you have sample access? Is it a posted pricing algorithm? What's even the benchmark? Like, so there are like many aspects of this problem, which are, again, like because of the vast list of applications it has, all of these aspects become important depending on which application you're in. And hence, this is like a very rich field. And like many of these topics we'll be touching during the workshop. So I've listed like partial list of like some of the talks that will be covering some of these topics, but yeah, so they're like many rich, and I'm saying like algorithmically it's like very rich. Hence, there are many open like questions that we have solved, and also many questions left to be solved. Good. Yeah, so this was basically the general spiel about the problem, but the focus of this talk is going to be, like, I want to say, like online resource allocation in settings where I can hope to get a 99% approximation. So when can I get a 1 minus epsilon approximation to the hindsight optimum, as if I was solving the problem offline? In what settings and what kinds of algorithms obtain such guarantees? So the focus of this talk is that how do we get these 1 minus epsilon approximation guarantees? And ideally, we want to even use a posted pricing algorithm to obtain this. That's the focus of today's talk. And as we'll see, like you need some kind of stochastic arrivals, like for adversarial arrivals and so on. Things can be really bad. I mean, there's no chance you can get like a 99% approximation. There are like simple examples, like maybe the first request gives you like $1, the second one gives you a billion, third one gives you a billion square, and so on. So the scale of the problem is extremely large. And at some point, everything in the future becomes zero for fully adversarial arrivals. And there's no way you can guess what the scale of the problem is.
So you can some divisible items.
Yeah, so I'll make the model formal in a bit, but yeah, so yeah, so it turns out it won't matter too much, like the kind of settings we'll talk about. We'll be talking about very general settings. But the major assumption we'll end up making is the large budget assumption, which basically means you have many copies of every resource. So roughly what it basically means is that if I'm aiming for a 1 minus epsilon approximation, I'll need every resource to have at least like 1 over b squared, 1 over epsilon squared kind of copies. So I'll assume like maybe no request is going to consume more than 1 unit of any resource. And I have at least like roughly 1 over epsilon squared copies. So I'll again formalize this, but basically I'm saying like under these two basically assumptions, like some kind of stochastic arrival and some kind of like large budget assumption, you can hope to get 1 minus epsilon approximation. And the next talk that Andres will be giving today will be more about in the smaller budget setting, where you can't get 1 minus epsilon, but depending on then a bunch of other things, accordingly, you can get like some constant approximation and so on. So the guarantees today will actually be true even for arbitrary monotone valuation. So I don't even care it's submodular, subadditive or something. It's even arbitrary valuation functions as long as it's monotone. Monotone means that say if I give you more resources, you're happier. The value will be happier. So that's the only assumption. Under that, basically, you'll get a 1 minus epsilon approximation. But in small budget settings, these things become more important. Like what's the valuation function? Good. So here's the outline for the talk. Like I told you what is online resource allocation, why it's like practically and theoretically very important. What are these posted pricing algorithms? Now we'll start first with like the simplest setting, which is I assume that these requests come from known independent distributions. So each request comes from a distribution, which is known to you upfront. You don't know the realization. The only hidden thing is the realization. So what happens and how would I go about solving this? Turns out like you can write a simple LP and perform a simple LP rounding. That already takes care of this setting. The problem becomes more challenging, which will be the next part, is the unknown settings, unknown distributions. Like what if you have unknown i.i.d arrivals? How you can go about designing, again, 1 minus epsilon approximations. And then towards the end, we'll talk about also like unknown independent distributions, but not identical. So how we can even still design some good algorithms there. Okay, so let's me formalize again now the model. So the model here is you have n requests. The ith request is going to come from some known independent distribution di. So the distribution is known to you. Think of it like it's like you have different kinds of submodular functions or some kind of functions, and the ith request takes one of these 100 possible submodular functions from some distribution. So different requests have different valuation functions, the value functions. The realizations are not known to you. As soon as the ith request comes, the goal is still the same. You have to select small theta I in the capital theta I decision set to get some value vi theta I, which is a non-negative real number, and you're going to consume some resources. And to make this large budget formula, I'm going to assume that the decision ai theta I, like it's going to consume at most 1 unit of any resource to set the scale basically. And then I'll assume that every resource you have at least like 1 over epsilon squared budget. So basically the point is that if you make a few wrong decisions, it should not hurt you indefinitely. So, and for many of these applications, real world applications, you actually have the large budget. It's not that you just have like one copy, you maybe have like similar, like large budgets for resources. And the question is about, exactly how you will maximize the value compared to the benchmark is in some sense, the hindsight optimum in expectation. Because optimum is also now a random variable. So I'm talking about the expected max, the maximum value. Good. And down the plan, as I was saying, is like I'm going to write a simple LP, like a very natural LP for this problem, as a warm-up, that how you can do write a simple LP and perform a LP rounding, and that already takes care of the setting. To simplify the LP a little bit, the notation, I'll assume that the distributions are somewhat simple, like the ith request takes like VI with some probability PI, and otherwise it's 0. So I'm thinking of like these are kind of like different kinds of requests. The ith request comes with probability PI, and if it comes, it's going to take some value VI. Otherwise, it doesn't come and its value is 0. This is just to simplify the notation. More generally, you could have like the ith request comes, it could take like 1 of 100 potential values and so on, and depending on the realization, those things. So, and now here's a very natural LP. So the LP just says the following: you have these variables xi theta, which in some sense kind of denote on average like how the optimum algorithm, the hindsight optimum in some sense, for the ith request with how much probability it's going to take this decision theta. So xi theta denotes this, and you'll write the most natural constraints, which is like the objective is to maximize summation over I and theta decisions, xi theta times vi theta, subject to your budget constraints, like xi theta, ai theta summed up should be at most your budget. I'll scale it down slightly by a 1 minus epsilon factor. This will be clear in the next slide, but roughly the point is when I'll perform randomized rounding to absorb standard deviations and so on, I have to slightly scale down the expectations so that the plus minus square root b error that you'll come from randomized rounding, that gets absorbed. So epsilon will be chosen to be roughly like 1 over square root b, where b is the budget. And you'll have the constraint that the final constraint is that summation over theta, like xi theta is at most PL, because the ith request only comes with probability PI. And as I'm saying, like you can again generalize this entire LP when you have non-Bernoulli kind of settings, ith request taking more, just that you'll have an additional summation over k floating around everywhere. So it just yeah, complicates the notation a little bit more, but yeah, nothing fancy. And yeah, so the simplest observation is that, okay, that this LP is immediately an upper bound on the optimum, the expected hindsight optimum, up to this 1 minus epsilon factor, because I've scaled down the budget by 1 minus epsilon. And everything is linear, so scaling down the budget by 1 minus epsilon hurts your value by at most, again, 1 minus epsilon factor. So up to this 1 plus minus epsilon factor, you are basically, this gives you a right bound on the optimum. So the goal would be, can I achieve this LP benchmark with 1 minus epsilon probability, like roughly the value of this? And my claim is this you can easily obtain just by randomized rounding. So what is online randomized rounding, or what is rounding? Basically is, once you know this LP and like the solution to this LP, it's basically at the ith request, you look at the value, the type VIK, and then I'm just going to take this decision theta with the probability given by this LP solution. So here I'm writing the solution even for general K, where, so in that case, you don't have variable xi theta, but xi k theta, where K denotes the kth type, like one of those 100 valuations. So you'll make this decision theta with probability x star ik theta divided by pik. Like basically you have to normalize it with the probability of this ith request coming and so on. And on average, you want to say that this algorithm is already going to be great. So any questions about the algorithm? Like I'm just saying, solve the LP and do the randomized rounding, just directly ith request takes this decision with this given by the LP solution. And as we'll soon argue, like simply by Chernoff bounds, this is going to be feasible with high probability, so you're fine. And the only slight thing which is kind of suboptimal about this algorithm is one thing is that it's not a posted pricing algorithm. I'm not really posting a price. I look at the ith request, I see what valuation K that they take, and then I'm going to take the LP decision. Hence, it's not a truthful algorithm, but if you don't care about truthfulness, then this is a good algorithm. And the reason this is like the claim is that this is already like a 1 minus epsilon approximation, as long as your budgets are at least 1 over epsilon squared times a log m. And why is this 1 over epsilon squared times log m is coming? Because basically log m you have to lose because you have to take a union bound over the m resources. And 1 over epsilon squared is just to absorb the standard deviation. So simply by Chernoff bounds, so that it suffices to argue that this algorithm works as long as your budget is not exhausted till the end. Like if you have resources available till the end, then any decision taken by this LP is going to be taken by your algorithm as well. Your algorithm does not halt early. And that happens as long as your budgets are available to the end. And simply by a Chernoff bounds, because in expectation, you are consuming only B times 1 minus epsilon amount. So you have this epsilon B slack. And if you set epsilon to be like roughly like 1 over square root B or something, then you can absorb the standard deviation. So simply by Chernoff bound, but you get a log m because you have to take a union bound, and you can show that in worst case kind of this bound is pretty much tight. Like you cannot hope to do anything better. Good. So this is going to be in some sense our like golden benchmark. Like we want to say that we can get a 1 minus epsilon approximation for any of these problems, even if the distributions are unknown and so on, as long as the budget is at least log m over epsilon squared. So that would be the dream. This is what I basically mean, the large budget setting here. Any questions? Okay, good. So if not, then by the way, yeah, so another remark about this LP, you might wonder, like, can I solve this LP in polynomial time? Turns out you can, although the LP, so okay, if everything is polynomial size, then of course you can solve it in polynomial time. But you can also solve it in polynomial time if the decision set is potentially exponentially sized. Like remember, like you're giving resources, and there are like applications such as auctions, combinatorial auctions, and so on, where the decisions could be every subset of resources, and there are exponentially many subsets. So the claim is you can still solve this LP as long as you're given the demand oracle, the oracle that I had mentioned you, where you can optimize this. The reason is that although in the primal LP you have exponentially many variables, xi theta, if you look at its dual LP, that will only have polynomially many variables. So all you need is a separation oracle for this dual LP. It turns out the separation oracle for this LP is nothing but the demand oracle. So you can define like these variables like lambda, j, and ui. They have some economic interpretations as well, like some kind of prices and utilities. So the separation oracle for this dual LP is nothing but the demand oracle. So as long as you can do the demand oracle, you can solve even the LP in polynomial time. But, yeah, so that's the observation. And yeah, these duals can also be interpreted as some kind of prices. So there are connections to prices as well, but let me skip that part. Okay, so the main takeaway from this first part of the second part of the talk was that for known independent distributions, if the distributions are known, there's a very natural LP. You can just do LP rounding. That gives you a 1 minus epsilon approximation, as long as the budget is at least log m over epsilon squared. It's not a pricing algorithm, and LP can be solved as long as you have a demand oracle and reasonable things. So the remaining talk is going to be what if the distributions are unknown and like support is large and so on, then how to get pricing algorithms. Good. So the next setup is identical distributions, i.i.d. arrivals, but unknown. And how do I get something again similar to budget being like at least like log m over epsilon squared, get a 1 minus epsilon approximation. Okay. So again, to clarify the model, n request, ith request comes i.i.d. from some unknown fixed distribution d. So the distribution is the same d. And immediately you have to set theta I to get some value and subject to the budget constraints. And the objective is the benchmark. So here's like a slight thing to be careful about, like why do I need i.i.d. versus independent? So in i.i.d. arrivals, because the future looks kind of the same as right now, like it's the same i.i.d. distribution. You can, in the beginning, maybe you don't know anything about the distribution, but as you go along, you can hope to learn something about the distribution and exploit that to get a value in the future. So for i.i.d. arrivals, this is true, but if the distributions are not even identical, then like you don't learn anything about the future. And hence you have to assume something more. Like, but for i.i.d., in some sense, like even for unknown distributions and like nothing is known, you can still hope to do a lot. And this is like one of the biggest problems that was like highly consequential. Small remark, all this thing that I'm going to tell is also going to extend to the so-called random order model, where you fixed some requests, but then they arrive in a random order, uniformly random order. So it's like sampling with replacement versus sampling without replacement. Some of the arguments become a little bit more technical, but everything can be extended to even this random order model, which is also sometimes called as the secretary model. So let me first give like a brief history. This is a very selective partial history on this problem in TCS in particular. So as I was saying, like this is like a very historical problem. It was already studied in optimal stopping theory from the 60s and so on, like the secretary problem and so on, which is the single resource setting. In TCS, Bobby Kleinberg had a paper in 2005, which studied the secretary problem for like large budget setting. He said it like multiple choice secretary problem, which is basically you're selecting rather than a single arrival, you're taking like B of them, which is the large, but the budget in some sense, and you want to maximize the sum. So this is the first paper. And then in parallel, like around 2005-10, like this is where like online advertisement was becoming extremely popular at companies like Google and so on. So people realized that there are some online bipartite matching settings, which are very good to capture those real world applications. So those problems were introduced. And Devanur and Hayes, like is one of the papers that realized that those problems, if you study them in this stochastic model, the i.i.d. model, then you can actually get a nearly pretty much the hindsight optimum, 1 minus epsilon approximation. So this is one of the papers. Again, like as I'm saying, like this is a very selective history. There are many papers in between. Then this like earlier papers were like Devanur Hayes was more about matchings. It was extended to general packing problems and general online resource allocation around 2010. And then there was extensions, like the initial papers did not get optimal bounds, but then people obtained near optimal bounds and also using pricing algorithms. So this was like a lot of activity that was going around back then. And like, yeah, in this tutorial talk, I'm in some sense kind of summarizing some of these results in this idea I will model. And as I was saying, like, yeah, this has been like very consequential, both algorithmically as well as practically. Good. So as a warm-up, let's look at the simplest setting of like basically Bobby Kleinberg's paper kind of a setting where you have n requests. Let's say these are just numbers. So you want to select B of these n numbers. Okay, so I want to say the problem n sequential arrivals. It's a single resource problem. So you have n budget B. You want to select B of these numbers to maximize their sum. And you can extend again all these things to, you can think of this some kind of a knapsack problem, online knapsack problem with budget B. And everything kind of extends. And the question is, how would I go about designing a good algorithm for this problem? And I have no idea about the distributions in the beginning. But as I go along, I hope to learn about the distribution and do something about it. Good. So how would I go about designing a 1 minus epsilon approximation for this problem, like a 99% approximation? And so the intuition is the following, that as long as I can find a threshold such that the expected number of elements above this, the expected number of numbers above this is roughly b, up to plus minus the standard deviation, so on, like plus minus square root b, then I'm good, because I can set this threshold and select any incoming request as long as they are pretty much like on average in the top b, or top b minus plus minus square root b. So the idea is that I want to learn a threshold such that the expected number of elements above this is b times 1 minus epsilon. If I do this, then I'm kind of done. And here's a very natural idea that you could do to learn this threshold is the following kind of like a two-phase algorithm. The first epsilon fraction of the inputs, just discard them. Don't take anybody. Okay, because anyways, you're willing to lose epsilon opt. So the first epsilon fraction will only contain like roughly epsilon opt of the value. These are i.i.d. arrivals. After the first epsilon n requests, you roughly expect, like out of the top b, roughly epsilon b of these top b requests will arrive in the first epsilon fraction. So if I, in the first epsilon n request, if I set a like look at the epsilon bth largest element. So the element which is like epsilon bth largest, that's going to be close to the bth largest overall. Like as long as concentration and all is taking care of things, as long as you absorb the standard deviations, basically the epsilon bth largest in the first epsilon fraction is going to be pretty much the bth largest overall. And that's what you do. Basically discard the first epsilon n elements, set a threshold, which is pretty much the epsilon bth largest in the first epsilon up to like a 1 minus epsilon factor, again to absorb standard deviation. And then for the remaining 1 minus epsilon n requests, just select any number which is above this threshold. So very simple, clean idea. And that already gives you like a 1 minus epsilon approximation. It's not optimal. It will require some budget guarantee, like roughly poly 1 over epsilon, like 1 over epsilon cube. But this already works simply by Chernoff bounds. You can argue that these standard deviations can be absorbed by simple Chernoff bounds. And you can actually improve this. And like that was Bobby Kleinberg's work as well. Like you can actually improve this to even get a 1 over epsilon squared, the tight bound. So remember, like in randomized routing, I was getting log m over epsilon squared. But now we are in a setting where m is 1. So basically that log m goes away. You just need a 1 over epsilon squared. And that was Bobby Kleinberg, what he showed, that the idea is roughly like rather than setting a fixed threshold after epsilon, do the standard trick. Like I'll use the first 10 requests to set a threshold for the next 10 requests. Then I'll kind of use the first 20 requests for the next 20, like the power of 2 tricks, then the first 40 for the next 40 and so on. So you just update this logarithmic many times and do a slightly careful analysis. And this kind of can be made to work. So this is like a simple idea of for single resource already pretty much solves everything in the i.i.d. setting. Again, any questions? I'm happy to take. Okay, so now the next thing is like, how can I extend this idea to multiple resources? Good, so extension to multiple resources. And this is what was done in like these papers of Devanur Hayes and Agarwal Wang and Yin Yu. So the paper was available of Agarwal and all from 2010. The journal version is from 2014. But they basically pretty much do the same thing. The idea is like rather than setting a fixed threshold, earlier I was trying to set like the bth largest element. I'm now trying to learn a price vector, a m-dimensional price vector, lambda, so a fixed price vector, such that in some sense, if I set this as a price vector and everybody performs greedily, like this demand oracle or whatever you want to call it, like the value maximizing step, then the expected number of any resources consumed is roughly p. You can show by like a primal dual argument, writing an LP, that such a price kind of exists. The LP that we wrote like in the last section, the dual of that kind of says that such a solution prices might exist. And that's exactly what you do. So this immediately gives you the corresponding algorithm. Again, discard the first epsilon fraction of your requests, solve the LP on the first epsilon n requests, but not with budget B, epsilon B budget, because you kind of, in the first epsilon fraction, you expect only epsilon B of your budget to be consumed by the optimum. So solve it again up to a 1 minus epsilon factor to absorb standard deviation. Look at the duals of that LP, set that as prices. And the claim is you'll again get an argument that 1 minus epsilon approximation, as long as your budget is like m over epsilon cube. So a few things to, first of all, this 1 over epsilon cube is the same 1 over epsilon cube that we had even for single resource. One thing to be careful about is why do I have a m factor instead of like log m is what we were dreaming for in the randomized rounding. And m is important. M is the number of resources. So for many, many applications like advertisements and so on, M could be very large. But naively, why you end up losing this factor M instead of a log M here is because the number of price vectors that you have in M dimension by some epsilon net kind of argument, you can say, is exponential in M. So you need to take a union bound over all of these exponential prices. You need to argue that you are able to discard bad prices from the good ones to find a good price vector. And that union bound basically loses like a log in this exponential in M, so which basically ends up losing a factor M. So that's the intuition to keep in mind. So it's a great algorithm, and these initial papers that already showed that at least for small budget, like if M is small, then M versus log M maybe is not so important. And this algorithm works. And again, you can combine it with, again, this power of 2, like 10, 20, 40, 80 trick to improve even this epsilon cubed to an epsilon squared. But the major drawback here is it's M over epsilon squared rather than log M over epsilon squared. So you can get a 1 minus epsilon approximation. And this is the part that will be the focus of for the next few slides. But any first questions, high-level questions? You're getting a 1 minus epsilon approximation. Okay, good. So next comes the algorithm, like which I'm saying, like gives you a 1 minus epsilon approximation, as long as your budget is like roughly like log M over epsilon squared. And this was obtained so the algorithm I'll discuss is in Shipra Agrawal and Nikhil Devanur's work. There were also parallel work by Anupam Gupta and Marco Molinaro, obtaining similar kinds of guarantees. And the reason I really like this algorithm is, first of all, okay, it's optimal and so on, but also like I find it very beautiful, like how it combines multiplicative weights and online learning ideas to set up these prices and use that to get basically optimal guarantees. Okay, so again, a high-level intuition if I have to give you, it's inspired from, some of you might have seen how to use multiplicative weights to solve like zero-sum games or packing LPs. You want to somehow use a similar idea that you want to come up with, like look at the dual of the problem and use some kind of a multiplicative weights idea to solve the packing LP. Of course, the problem is a bit different because you're in an online setting. It's not, you cannot directly apply the old algorithms. So you have to make changes, but at a high level, intuition is similar. Okay, so first of all, let's quickly recall what's multiplicative weights. I assume like many of you have already seen, it's again an online problem where you have n rounds and you have m experts. Think of them as like sitting on a simplex, like these are the vertices of a simplex, and each round you are going to play a distribution over these m experts. And I'll work in the solid simplex in the sense that you're allowed to go, this need not to be sum up to exactly 1, it could be less than equal to 1. It's not exactly a distribution, like summing up to at most 1. And each round you play some distribution over these experts. Then you get to see some reward Ri in the ith round, which is a bound, like plus minus 1 bounded reward. And the reward that you achieve is basically the dot product of the two. And your benchmark is the best fixed disease, best max overall J, EJ, best expert in hindsight. So what can you do for this? It's in some sense very similar to online algorithms that I guess we've been talking. Like a major difference here is you first make a decision and then you get to see the ith request. And so that's why also like you get kind of regret. But the multiplicative weights is like a classical algorithm, which shows that even for this problem, you can get, with respect to this benchmark, you can get a sublinear regret. So you have a regret, or like basically the difference from the benchmark is square root benchmark of the order of square root benchmark. Okay. The only thing here is maybe some of you might have seen it in terms of square root n instead of square root benchmark, but you can show that the same analysis goes through instead of square root benchmark instead of square root t, like, or square root n. And the algorithm is like some kind of exponential weights, like where you are going to maintain some kind of a distribution over these experts, and depending on their rewards, you're going to exponentially adjust it proportional to how much kind of they're achieving the rewards. And this kind of an algorithm works. So I'm going to assume this. Now the question is, how do I use this multiplicative weights idea to design an algorithm of Agrawal and Devanur to solve our online resource allocation problem? And here's the main intuition, and I would say like this is like the most important intuition of this talk. So the idea is the following. So remember, like we're trying to play some prices. So they basically say the following, like this algorithm says that I want to play a price vector. Like I want to come up with this price vector such that on average, if I play this price vector, the amount of resource that you're consumed, any resource that will be consumed in a single step is going to be B over N. So remember, your total budget is B. you have n arrivals, i.i.d. arrivals. In a single time step, because you should be consuming ideally like b over n, because everything is like on average, because all time steps are identical. So the idea is the following, that, okay, I want to find a price vector such that on average, I should be consuming in any step b over n budget. And if I'm consuming more than this, then in some sense, I should be increasing the price of that resource, because that resource is being over demanded. And if I'm consuming less, then I should lower its price. So the intuition is that, think of the dual problem, where I want to play a price vector. I want to see how good the price is. Of course, the challenge is I never get to see exactly how good my current price is, but you can get an unbiased estimate of it. Just look at the next arrival. It's an i.i.d. fresh sample from the same underlying distribution. Just evaluate your current price vector for this fresh request. It's an unbiased sample. And you can use this intuition to basically give you that, okay, am I consuming b over n, or am I consuming less or more? And that's precisely you'll do. So the algorithm is precisely just formalizing this. So, and for simplicity, let's assume all resources have the same budgets, because otherwise the notation becomes a little annoying. Also, let's assume that I know roughly the value of opt, the overall global opt. I know it. That's again, like by discarding the first epsilon fraction, you can easily argue by concentration bound that you can learn the value of opt. So it's not a big assumption. So let's assume this. And now here's the Agrawal-Devanur algorithm, like the multiplicative weights algorithm. It says the following. In each round, the multiplicative weights algorithm is going to give you some distribution, yi. The prices I'm going to play are not yi, because remember, yi is a distribution. Prices are in some different units. So I need to kind of convert the unit. So I just scale it by a factor of opt over b. Because this is just some kind of a scaling in some sense. Think of this as like change of units. So I'm converting this distribution to prices. So the prices I'm going to play is basically whatever the multiplicative weights say, scaled up by opt over b. And then what do? Like you play this price, look at the best response for the next request, like this i.i.d. request that comes. In case any resource gets exhausted, I'm just going to stop my algorithm. But otherwise, I'm just going to use multiplicative weights to update the prices. And what's the reward? Is basically how much resource I consumed jth request. So ai theta I of the jth coordinate minus the bj over n. So the reward, basically, the most important thing is this feedback is the reward that you consume minus b over n. So that's kind of how you're going to, there's going to be the feedback. And again, the point was that if you are consuming more, then your resource price will increase. Because what will happen is basically this expert corresponding to this resource will get higher reward. So your multiplicative weights algorithm will increase the weight of this expert. And increasing the weight means it's going to increase the price of this resource. That's the algorithm. So it's a very natural algorithm, but yeah, it's somewhat like very interesting. And yeah, so and the claim is that this algorithm basically gets you like 1 minus epsilon opt. And it only requires budget to be like log m over epsilon squared. So maybe yeah, okay, at least. So one small observation is that the regret term that we had, that's first I want to say that the regret term is pretty small here, because for this problem, the rewards you're getting is like ai theta, like the amount of resource that you consume minus b over n. Summed up over all time step, the opt is going to be only of the order of b. Like b is the budget, total budget. So if you calculate this, like put opt over b times regret, that's going to be roughly epsilon opt. Like the way I've chosen the parameters, one can do the simple calculation. But the point I'm making is regret is basically of the order of epsilon opt. So let's imagine regret is basically 0. And so regret doesn't matter. And now the analysis. So again, the analysis, as I'll do, like it will fit entirely in the single slide. But I can imagine like, okay, it might be a little hard to digest it. It's not doing much. Like, so I'll basically go over it a bit quickly. But all it requires is like a simple three inequalities. You just have to use like somehow the greediness, the fact that you're doing best response, and somewhere you have to use the no regret property. So what's the algorithm, the analysis? It's like algorithm is getting all the values vi theta up to some time stop tau. Tau is the last time before your algorithm halts. Like maybe it runs out of any budget, any resource. And in case it never runs out of any resource, then tau is basically n, like till the end, it goes on. And I'm going to plus minus subtract. Like, so value is vi theta. I'll go into plus minus lambda ai theta. I'll apply the greedy step because I was always doing the best response. So I could have replaced this theta, the action that my algorithm took, with whatever the LP would have done. In some sense, the hindsight optimum kind of a decision, theta is star. I could have replaced this because this was a valid choice. I could have done it. So this is a valid inequality. And then I'm just going to like, again, plus and add and subtract this minus b over n term, just because this is how things were set. And you can argue immediately that in expectation, this middle term is going to be basically 0. This is basically because in expectation, the optimal choice theta I star, expectation of ai theta I star is nothing but b over n. And that's the reason you can kind of cancel this term. There's like a slight catch that why can I move the expectation inside? Because of i.i.d request, you can say that it's independent of lambda I. So expectation can be moved inside. And so on, like again, like some subtlety, but all I'm saying is the middle term can be ignored. And so you're basically just left with these two terms, like the first and the third term. And now, depending on the two cases, whether you are in case, like whether you go on till the end or you stop early, you have to apply accordingly the no regret property. So let me just first flash. So this is the entire proof. So you have two cases. Case one is where you go on till the end. In this case, you apply no regret property with respect to the all zero price vector. So that's the reason I was working with the solid simplex rather than just the vertices. Like, so you apply just the no regret property because somehow you're saying that, okay, if you're never consuming all the resources, I mean, there's like all zero was an option, like playing zero price. I mean, so you have to apply no regret because in some sense, like even trivial prices are not doing much. The other case is where you exhaust one of the resources. In this case, whichever resource you exhaust, like you exhaust the jth resource, I'm going to apply no regret with respect to that ej. And that's it. And otherwise, like simple algebra and manipulation. And you can argue that both cases you get 1 minus epsilon. And that's basically the entire proof. Again, I don't expect you to maybe follow the calculations online, but yeah, it's nothing. The only things that you have to apply is the greedy inequality and the no regret. Okay, so here's the main takeaways from this part of the talk. So first we saw like a simple idea of if you are willing to lose, like instead of log m over epsilon square, if you're fine with m over epsilon square, you can do a very simple argument where you ignore the first epsilon fraction, set the dual prices or dual thresholds, and that already gives you a decent guarantee, m over epsilon squared. The second approach, which is much more algorithmically interesting and also optimal, is via this multiplicative weights idea, where you get the optimal guarantees like log m over epsilon squared. And the main idea, again, the crucial idea is how you are going to use this multiplicative weights idea, multiplicative weights algorithm to update these prices, these dual prices, where the intuition is that I want to play a price such that in expectation, every resource is consumed B over N. If you're overusing it, then you should increase the price. If you're underusing it, decrease the price. Okay, any questions? Like this was the most, I guess, the main technical part. And like in the next 5 minutes or so, I'll basically conclude and talk a little bit more about some other extensions. Okay, good. So finally, like let me quickly talk about like what happens for non-identical distributions, independent but non-identical distributions, and which are unknown, and how to get something like a 1 minus epsilon approximation even in those settings. So the setting is like, as I'm saying, n requests, ith request comes from an unknown distribution di. You have to immediately set theta I, and you have to maximize expected value and generalize. So as to maximize total value. And this is a generalization of, you can think of some kind of profit inequalities, the classical profit inequalities from optimal shopping theory, which is usually thought of as like a single resource problem. And of course, for unknown distributions, non-identical, in general, as I was saying, you cannot do anything because these could be like point mass distributions and you have no idea this. So it's capturing basically adversarial arrivals. And for adversarial arrivals, you cannot hope to get a 1 minus epsilon approximation. So the assumption one has to make here is that I'm going to give you a few samples from the underlying distribution. So I don't know the distributions, but I'm going to give you like, say, 100 samples from each of these n arrivals, like a few samples from these arrivals. And now I want to use these samples to get a good algorithm. So these are like underlying samples, like basically real world motivation is more like you've collected some historical data, you treat that as some kind of samples, and you design a good algorithm. Okay, for identical distributions, this didn't matter because you can learn as you go. For non-identical distributions, you cannot hope to learn as you go because future could be very different from the past. But this is where you have given a few samples. And now for this setting, again, the main question is how to get a 1 minus epsilon, ideally a posted pricing algorithm. And what if we have sample access to these distributions? So this is some very recent work that I have with Rohan Koke. He's a postdoc with me at Georgia Tech, and Yifan Wang, who's a PhD student again at Georgia Tech. So we basically get again a 1 minus epsilon approximation, as long as your budgets are again the same, like log m over epsilon squared, but you require some poly 1 over epsilon samples, like polylog over epsilon samples, polylogs over epsilon. The exact sample complexity is still open, but we are able to get at least like poly 1 over epsilon samples suffice. And so I'll maybe briefly say like what the algorithm is. The algorithm is in some sense very much the same algorithm as the Agarwal-Devanur with one twist, one major twist. So the idea is the following. We call it the exponential pricing algorithm. So the setup is pretty much the same. Like you are again going to play a price vector each round. You're going to, and the algorithm is going to take the best decision with respect to the current price vector. And now I'm going to update the prices. The question is, how do I update the prices? So again, I'm going to look at ideally what I wanted. Let's say for a moment, I'm in a setting where I know the distributions. So in the ith request, whatever my LP says is the expected resource consumption for that ith request. That's in some sense my target. So my current price vector should be consuming that expected price vector for the ith request. So let's say I know the LP. Otherwise, I mean, if you are given samples, you can estimate some of these things. And turns out that can be also made to work. So the idea is basically you play a current price vector. You want to update the price as the difference of how much resource you consume minus whatever is the expected prices. So this is the same thing as we were doing earlier. Expect AI theta I minus, earlier we were putting B over N because the expectation was the same everywhere. So it was exactly B over N. But now this expectation could be different for different time steps. These are non-identical distributions. So that's one difference, but that's like somewhat natural. The other major difference is that this is an equality and not a proportionality. So in the multiplicative weights algorithm, you actually maintain a distribution over these experts, or maybe like over the simplex, solid simplex. Here we are actually maintaining an equality. So in some sense, you're saying like the sum of the prices could increase exponentially as time progresses. Whereas in a multiplicative weights or any of these other algorithms, the sum of the prices remains kind of the same, or like pretty much the same. So this changes the entire thing. Like it's no longer a no regret algorithm. You don't have the no regret property because you're not maintaining a distribution and so on. It's not a multiplicative weights algorithm. In multiplicative weights, you have a proportionality constant here, proportionality factor here. Here I have equality in this algorithm. Turns out this can also be made to work. Like now we have to exploit some of the properties of the problem, the particular problem. So the analysis is somewhat similar to what we were doing earlier. Like again, you have algorithm is summing up from I equals 1 to tau. You do the same step, subtract off this consumption, do like slight adjustment. And again, you're left with like first and the third term. The second term can again be shown to be 0. The first major difference is earlier we had two cases, whether your budget is exhausted early or your budget is available till the end. But now I'm claiming that your budget will always be available till the end. The reason is, if your budget ever gets exhausted earlier, because your prices are increasing so fast, if you try to consume your budget early, I am going to say your prices will be more than the value of opt. So you automatically get the value of opt. So what this advantage of this exponential pricing is that rather than having two cases, it reduces the problem to one case because the other case becomes trivial. If you stop early, you're already getting more than opt value because your prices have increased so much. So that's the benefit of this part. The challenge, of course, is now you don't have the no regret property. Interestingly, what we can show is you can exploit the structure of this exponential prices to show that it still has no regret property just with respect to the all zero vector. So it's not no regret with respect to everything in the simplex or anything. You can still exploit the structure of this thing, prices, to argue that you have some kind of a no regret property just with respect to the all zero vector. And the other case, the only case that we have to consider out of the two cases, there were two cases. One case we had to use no regret with respect to the all zero vector. Another case we had to use with respect to the resource that's consumed. That case is already gone. So all we need is the no regret property with respect to the all zero vector. And that you can show still kind of holds some form of no regret property, and this can be formalized and so on. So again, I don't want to say more about this, but yeah, it's like some very recent work. Good. Any quick questions before I conclude? Okay, so here's the summary. I guess, yeah, we thought a lot about online resource allocation, why it's so useful both in practice and algorithmically. It's so rich. We saw a bunch of settings where we can get a bunch of ways of getting a 1 minus epsilon approximation, as long as your budget is reasonably large, like log m over epsilon squared. Another great thing was that all of these were like the algorithms that we designed were often posted pricing algorithms, which are both practical as well as like truthful and like many other benefits they have. And the crucial ingredient was some kind of a low regret property, no regret algorithms, connections to online learning. Some open problems, if I have to say, like specific to this talk, were more about like for known distributions even. First is like we were always updating prices. Like we still have limited understanding of static prices, like fixed prices, where you're not allowed to update prices. And depending on the application, like maybe say airline industries, every day you take the flight, the prices get updated. But there are some settings where you cannot really update the prices. So we still have somewhat limited understanding of fixed prices settings. Other is for the unknown setting, like we are getting log m over epsilon squared, which is tight in general, but turns out for some problems such as matchings, you can actually remove the log m. It's not log m over epsilon squared for matchings. For matchings, it's still like 1 over epsilon squared if you do LP rounding. And the reason is because for matching, when you do a allocation, it's going to consume only one of the m resources. It's not going to consume multiple resources simultaneously. This is called as sparsity, like how much resources you're consuming, the number of resources, it's called sparsity. So ideally, in an ideal world, you would want log of sparsity over epsilon squared rather than log of m over epsilon squared. All these results currently get log of m over epsilon squared using prices, whereas LP rounding and some of these other things would suggest you would even hope to get a log of sparsity over epsilon squared. That's again something to understand. And then there are also like tight sample complexity and so on. That's somewhat less understood. And again, like during the workshop, we'll be talking about many other aspects of the problem, some robustness properties and many other, and all of them have like many open questions. And Andres will be next speaking about online resource allocation with small budgets. But that's it for today for this talk. Thank you. Okay, let's take like a 5-minute break and then we can resume at 10:05.